Okay, so I want to give a very brief introduction to several different experiments that we'll have on the top of Casper Mountain in Wyoming. And the motivation behind this is to understand the magnetism of the sun. We know that the magnetic field is generated in the sun's core, and as the sun rotates, the magnetic field rises to the surface and then emerges into the atmosphere. And that results in the active regions that we see. Now, sometimes these active regions can be relatively benign, but other times they can erupt. They cause flares, coronal mass ejections, but we really suck at being able to predict when these things will erupt. And being able to predict them is really important, because if they are directed towards the Earth, then they can have a profound effect on us. And the main reason why we have such difficulty in predicting when these eruptive events will happen is because even though they're driven by the magnetic field, we really cannot measure the magnetic field in the corona very well. What we can do is measure the magnetic field in the photosphere and then use models that predict what the magnetic field would then look like in the corona. But these models don't always do such a great job. And so to really get a handle on predicting eruptive events, we really want to be able to directly measure the magnetic field in the corona. But this is difficult for one reason, is that the magnetic field in the corona is very weak, but also the photosphere is about 1 million times brighter than the corona, so it just drowns out measurements that we try to make. So the Eclipse will solve one of these problems by occulting the photosphere during our measurements, and we hope to solve the other one by measuring the infrared spectrum of the solar corona. This part of the spectrum is the most sensitive region of the sun's spectrum to the magnetic field. And we're going to do this using the NCAR airborne interferometer, which was originally designed to fly on a scientific aircraft. And we've repurposed it to be able to observe the eclipse from the ground. And this is the setup in the lab. But what this will do is give us a full spectrum of the infrared solar corona from around about 1 to 6 micrometers, which has never been measured before. So these will be new measurements. But the problem with this instrument is that it integrates the light over the entire corona. So we don't know which part of the corona is contributing which part to the measurements. So the way to solve this problem is to combine it with an imaging camera. And we're going to use an infrared camera from FLIR, which we have tested in the lab. And so far, we have been able to confirm that it can successfully image a hand and a motorcycle. And I'm confident that it'll also successfully image the corona. Okay, so this will give us images and spectra of the corona, but to actually measure the magnetic field itself, we need to know about the polarization of that light. The magnetic field in the corona causes the light to be polarized in a certain way. We normally can't see that polarization, but some animals can. And 4D technology has developed a camera based on the funky eyes of the mantis shrimp. So this camera works with having an array of detectors that measure different polarization angles simultaneously. And when we measure that polarization, we can then infer the magnetic field strength and direction. So this camera and the infrared camera are both small, kind of handheld size. They can easily be mounted on the back of our relatively simple telescopes. And then we will just take all of this equipment, throw it in the back of a van, and drive 4 miles north to Wyoming, to our eclipse site, which is near Casper. And we'll be at the top of Casper Mountain, which is around 8,000 feet. So being at high elevation reduces the effects of the Earth's atmosphere absorbing the sun's light. And we will have our 3 experiments set up next to one another, so we will have simultaneously spectra, images, and polarization information from the sun all at the same time. So I like to think of this as one large experiment consisting of 3 individual components. And hopefully this will go some way to helping us being able to predict flares, CMEs, and other eruptive activity from the corona. So I want to just kind of finish with one quote that I like. And I know I'm kind of preaching to the choir in this room, But if you know anyone that is not particularly excited about seeing totality, or thinks, oh, I've seen a partial eclipse, I don't really need to see a total eclipse, then I think this quote from Annie Dillard kind of gives a good explanation of why you should really see totality and not just be happy with partial eclipse. And I'll leave that up there for you to read. Thank you.